Hello, and welcome to Unit 2, which will cover multivariate calculus. Today, in this lecture, we're going to be talking about derivatives. So we're going to cover the basics of those, what they entail, what derivatives are as a concept, some rules about how to calculate them, and then eventually we'll build up to partial derivatives. So let's go ahead and dive right in and get started. Before we begin, just an overview of what we're going to be covering in Unit 2. This first lecture is going to be on derivatives. We're going to build up on that and go to integrals or the antiderivative. Combine those concepts and talk about gradients. And gradients is going to be an exciting lecture. We're going to expand those to higher dimensions. And then finally, we'll use all of that to cover convex optimization. And that is ultimately what's going to be important to understand for machine learning. So why calculus? Well, if you look at this graphic here, you'll see the typical artificial neuron, what you would normally see in a neural network. And so on the left, we have our inputs, x1, 2, all the way to n, multiplied by the weights with the dot product, summation of those, plus the bias times an activation function to produce the activation. So this is what goes on in a deep neural network. The premier network used for artificial intelligence. And to optimize this, we have to update the weights, W1, W2, all the way to Wn, after each iteration to improve the performance or reduce the loss of our network. And that is accomplished using gradient descent. And gradients are going to be calculated with multivariate calculus. So derivatives go into that. Integrals aren't going to come up as much until we get to probability theory, and then we're actually going to see integrals in the context of probability. But derivatives and gradients are ultimately what gets used to improve the performance of neural networks. So they are the learning in the machine learning, and that is why they're going to be very important to cover. And it's ultimately not going to be entirely important to understand how to take the derivative in every single case for all these different kinds of functions, because we can talk about derivative rules for a long time. However, what is going to be important is understanding the concept of a derivative, how it works, and what you're actually calculating when you take a derivative. So that's what we're going to talk about first, derivative concepts. And so the definition of a derivative can really be understood in two different ways. The first one is in a geometric perspective. And in this perspective, the derivative is going to be the slope of a curve. So if we had a graph of a simple curve and we drew a tangent line at any given point along that curve, that would be the derivative of that curve at that point. So taking the derivative of a curve will give us the slope of that curve. And this is a good way to understand a derivative from a geometric perspective. It's a slope or a tangent line. Essentially, it's going to be how much the curve is changing at that particular point. And that kind of lends itself to the other concept that you can think of this is, and that is a physical concept where the derivative is the rate of change. So often this is how you would look at it from perhaps a physics perspective. If you had an equation describing the displacement of an object, if you took the derivative, you would get the velocity. So the velocity is going to describe how quickly an object's position is changing. So it is the rate of change in that sense. And then actually you could take the derivative of the velocity and you get the acceleration. Acceleration is the rate of change of your velocity. And so in that sense, you can understand the derivative as the rate of change of any given function. You take the derivative and you can find out how fast or in what direction the equation is changing. So two ways to understand a derivative here. Both are equally valid. You have a geometric perspective and a physical perspective. Both of them ultimately, though, come back to change. The derivative is going to tell us how something is changing, in what direction it is changing, whether that is a rate of change or the slope of a curve. Ultimately, they are going to be telling us in what direction and by how much is an equation changing. All right, so that's the basics. Here we're going to talk about notation a little bit. So the derivative operator is typically written as d over dx, and the d's just imply derivative. The x on the bottom is actually going to tell us what variable we are taking the derivative with respect to. So this could be said as the derivative with respect to x, or d dx is just a quicker way to say it. And there's a couple ways to write this. If we had the function y equals f of x, then we could say dy dx. That would be the derivative of y with respect to x. We could write this as df of x over dx, the derivative of f of x over with respect to x. And then you can write it either way. You can have the f of x in the numerator there, or you could write it off to the right. And one last way that you can write the derivative is with a prime. If you see f prime of x, this is going to be the derivative of f of x. And so f prime of x is the same as d dx of f of x. That is also another way to write the derivative. Okay, so that's the notation. Let's talk about a few scalar derivative rules. And we're certainly not going to cover them all, but it is important to understand the basics. First things first, the derivative of any constant is going to be 0. So for example, the derivative of 62 with respect to x is simply 0. And this is ultimately because there's no x variable in this constant. So that just goes to 0. And that makes sense if you think about our derivative concepts as the derivative being the rate of change. 62 by itself is not changing at all. If you think of the graph of just 62, it would be a straight horizontal line at y equals 62. The slope of that is going to be 0. So from either perspective, either concept, we are going to intuitively know that the derivative of constant is going to be 0. The next one is the power rule, and this is probably the most important one. This is how you take care of variables in your derivatives. So if we have the derivative of x to the n with respect to x, we're going to calculate that by taking the power. We take the exponent and multiply it in the front, so that's why the n comes down, and then we subtract 1 from the exponent. So for x to the n, we're going to get n times x to the n minus 1. So let's look at our example. The derivative of x to the third with respect to x, you're going to take that exponent 3, multiply it in the front, so you get 3 times x, n minus 1. 3 minus 1 is going to be 2, so we get 3x squared. And so the power rule is probably the most commonly used rule. These are going to come up a lot, but since we're going to have variables in the equations that we want to take the derivative of, this comes up almost every single time. So bring the exponent down into the front and then subtract 1 up at the top. Next, we can talk about multiplication a little bit. D dx of c times x to the n. We can simply bring that constant or coefficient out into the front. We don't have to worry about it when taking the derivative. So you can see I have written it as c then times d dx of x to the n, which is going to follow our normal power rules. So the exponent n comes down, and then we have n minus 1. So for example, if we have the derivative of 4x to the third with respect to x, we can simply bring that 4 out into the front. And then our x to the third is going to follow the same power rules that we had up above. So that exponent 3 comes down, and then we get an n minus 1, an exponent of 2 left over. So we have 4 times 3 times x squared, which is going to give us a derivative of 12x squared. So multiplication is really important because we're going to see, especially in regards to partials, if we have constant coefficients that are being multiplied by our variables, we can bring those out into the front and then worry about adding them back in later. All right, we can actually move on to a few more derivative rules. Again, as I mentioned, we're not going to cover it all, but some of these are important. So we have the sum rule. If we have two functions and they're added together, we can take the derivative of both of them individually. So if we had an equation like x squared plus 2x, we could take the derivative of x squared and 2x individually. So here's an example of that. We have 4x plus 2x, and if we wanted to take the derivative or 2x squared, if we want to take the derivative with respect to x of this entire function, we are going to individually take the derivative of 4x and individually take the derivative of 2x squared. Notice we're following the multiplication rule, so we have taken those coefficients out into the front. The 4 comes out in front of the d dx. And then also this 1x, we've written it as x to the first, since just x really does have a power of just x to the 1, or x to the first. And then we can help follow our power rules here. So if you notice, we'd multiply the 1 into the front, and then you'd follow the power rule. You have n minus 1. 1 minus 1 is just going to be 0. So essentially, we're going to have 1 times x to the 0. Any variable to the 0th power is going to be equal to 1, so that essentially just drops out, and we're left with the 4. And then for the second half, the 2x squared, we pull the 2 out in front of the d dx. The derivative of x squared is simply 2x, and so 2 times 2x is going to leave us with 4x. Ultimately, we get 4 plus 4x. So the product rule, if we are multiplying two functions together, it gets slightly more complicated. What we're going to do in this scenario is the derivative of the first times the second plus the derivative of the second times the first. And that's what you see in this formula here. If we have f of x times g of x, we're going to start by taking the derivative of the first, that's the d dx of f of x, multiplied by the second, times g of x, and then plus we'll add to that the derivative of the second times the first. So we're taking the derivative of both and then multiplying it by the other function and then adding them all together. So let's look at an example. If we had x squared times x, and I know we could combine these to start, but let's just view them as two separate functions for the purpose of this example. If we wanted to take the derivative of that with respect to x, we would follow our product rule. So we do the derivative of the first, which is x squared, times the second. So we have x times the derivative of x squared with respect to x. And then we add to that the derivative of the second times the first. We're going to have the derivative of x with respect to x times x squared. So going through those derivatives, the derivative of x squared is simply 2x multiplied by x. And then we add to that x squared. And remember, the derivative of just x, since this is going to be x to the first, is just 1. So we're left with just the x squared. And then multiplying those together, we get 2x squared plus x squared, which ends up being 3x squared. And this makes sense because if we actually combined the x squared and x before taking the derivative, we'd have x to the third, and the derivative of x to the third is going to be 3x squared as well. So that all checks out. So those are all the rules we're going to cover. We are going to talk about the chain rule a little bit, and then we are going to move on from these rules. Again, you don't need to know all the rules. There are many. How to handle every kind of function in all these different types of scenarios. However, we're just covering the main ones so that we can have a better understanding of what the derivative is actually doing. So this is the chain rule, and this is actually a very important one for machine learning, because when you have multiple layers, you're going to actually have to use this to calculate the derivative of earlier layers. And so if we have a function g of x inside of another function f, what we're going to do is we're going to take the derivative of the outside function, and that is denoted with the f prime here, and then we're going to multiply that by the derivative of the inside function. So this is easiest understood when looking at an example. So let's go through that. Here we have the function sine of x, and inside of that we have the function x squared. So here f of x would be the sine of x, and then the g of x on the inside is going to be x squared. We're not going to cover the trig rules, but the derivative of sine is actually cosine. So that's the f prime is going to be cosine, and see we leave the g of x, so we have cosine of x squared, times the derivative of the inside. The derivative of x squared is, of course, a 2x, so we're left over with 2x times cosine of x squared. So this is the chain rule. Again, very important when calculating the derivative of earlier layers in deep neural networks. And again, the computer is going to be able to do most of these for us, so we're not going to be worried about the functional aspect of actually solving these ourselves. That is what deep learning libraries are for, and computer programs like Python will do that for us. All right, so now let's move on to partials. So partial derivatives are going to be used for equations with more than one variable. Very rarely in machine learning are we actually going to have only one variable. So earlier I mentioned in the denominator the dx refers to the variable that we are taking the derivative with respect to. So if we have d dx and d dy, we're going to have the partial with respect to x, and we're also going to have the partial with respect to y. So these are partial derivatives, and they are used for equations that have both of these variables in them. So let's go ahead and take a look at an example. If we have the function f of x and y is equal to 3x squared y, we're going to have to use partial derivatives. So to start, we can take the partial of f of xy with respect to x. And when we're taking the partial with respect to x, what we are going to do is treat the y variable as a constant. So this is now just a coefficient, and it's going to follow all of the same rules that we just talked about. Specifically, it's going to follow the multiplication rule. So what we can actually do is we can move that y as well as the coefficient 3 out in front of the derivative and just take the partial with respect to x of the x squared. So now we have 3y multiplied by the derivative of x squared with respect to x, which is simply going to be 2x. Multiplying the 3 and the 2, we get 6xy is going to be the partial of f of x, y with respect to x. On the flip side of that, we can take the partial of this with respect to y. So now, exactly the same derivative rules as we were using for x, it's just a different variable. We can treat the x squared as a coefficient. This is just going to be a constant, and we are only going to worry about the y when taking the partial with respect to y. So now we can move that 3x squared, because those are both constants, out in front of the d dy, and now we have just the derivative of y with respect to y, which of course is just going to be 1. So we're left over with 3x squared. So these are the partials of this function with respect to x and respect to y. So not too difficult. All you have to do is treat the other variable, all other variables, as constants when you're taking the partial with respect to a particular variable. This is just two variables. We're actually going to see in a couple lectures that this can quickly get expanded to more and more variables. So we could have an equation of 10 variables, and then we would have 10 different partials that we can take. So if you don't feel very comfortable with this, I would recommend covering some more practice. There will be a question on this in the unit quiz, of course. However, we are covering this really quick. Calculus is semester-long courses, and so if you feel like you need some more resources on this, I would encourage you to dive into it deeper in perhaps Khan Academy or some online textbooks. This is basic calculus, so it is covered extensively in a lot of different resources. So there are options out there for you to learn this more thoroughly if you desire. But in the context of machine learning, we are going to move through it pretty quick because we really only have to understand the concepts. All right, so that brings us to the conclusion of this introduction to derivatives. In the next lecture, we're going to talk about integrals, which are going to be essential when we're talking about probability and probability theory and the actual outputs of different deep neural networks and other machine learning algorithms that are critical for artificial intelligence. I hope you learned something today about derivatives, and I hope you continue to listen to the next lecture. Thank you very much.